discussed about the definition and formula for position of center of mass of a system of particles. So for a discrete particle system, we had seen that the vector notation for position of center of mass was given by the relation that the position vector of the center of mass, we can write it as RCM or RCA, whatever, that is the weighted mean. So that is a summation. So because it's a weighted mean, it is summation of mass into position divided by summation of mass or total mass. So this is for an n particle system. So we see that position vector of center of mass is the weighted mean with respect to mass of the position vectors of the particles of a given system. So on the basis of this, we had done a few questions last time. So today also we'll start with a quick revision question to quickly understand once more the application of this kind of concept and formula. Okay. Yeah, Jitesh, the summation converts into an integration when we have basically a continuous mass system instead of a discrete particle system. But in the case of discrete particle system like here, we have to express it as a summation only. Okay.
So
Yes.
in second part of center of mass, we will have to take it as
Yes, when we come to continuous mass distributions, we will see that it will convert into an integration. Okay.
Yeah.
Okay, so let's look at a quick example. 4 particles E, which has a mass of 20 grams and position B, which has a mass of again 20 grams, but a position of this C, which has a mass of 50 grams. D, which has some unknown mass and which is located at some unknown position in terms of the y coordinate. So 4 particles form a system such that their center of mass is at the origin. So we have to find from this the mass of the 4th particle and the y coordinate of the 4th particle. So this is very similar to a sum we had done last time. You have to just apply the above formula and understand how you can find 2 unknowns from application of the same formula. Yes, people. So I'm just going through the answers sent by you. Most of you have got it correct. Very good. Okay, so all you have to do here is apply the formula that if you convert the above vector formula into coordinates, RCM is summation MR divided by summation M. In terms of coordinates, it becomes x coordinate of the center of mass is summation mx by summation m. So here, if we apply that situation to this, the x coordinate of the center of mass should be 0. So that means summation mixi should be 0 because the center of mass is at the origin. So 20 into 3 plus 20 into minus 2 plus 50 into minus 1 plus this unknown mass into 2 should be equal to 0. This is the equation that we have. So 60 minus 40, that's 20. Okay. Minus 50, so 30. So that tells me that mass of D is 15 grams, which most of you have worked out correctly. So now next thing is y coordinate of the center of mass is also 0 because here the center of mass should be at 0, 0 or origin. So summation my should be 0. So 20 into 2 plus 20 into 1 plus 50 into minus 4 plus 15 into some y should be 0. So this will give us 40 plus 20, 60 minus 200.
28 upon 3.
Minus 140 plus 15 yd is 0. Okay, so very straightforward and easy, nothing difficult here.
Yes.
Okay, so hope this question is clear. Now moving on to the next part. So last time we had just about started with the discussion about motion of center of mass, and we had seen how to derive a formula for displacement of center of mass in the case of a two particle system. So we'll generalize that now. So we'll see that if we have a many particle system, n number of particles, and at least some of them are in motion, at least more than one, I mean, at least one or more are in motion, then the center of mass will also be in motion. and how to calculate the various parameters like displacement, velocity, etc. So motion of the center of mass for a moving system. So by moving system, we mean that at least one particle within the system should be in motion with respect to some kind of reference frame. Then we can say that the system is in motion and therefore the center of mass is most likely in motion. So starting with displacement of the center of mass. So displacement is defined as change in position. So here it is change in position of center of mass. In general, that is a definition of displacement. The vector definition of displacement equals the change in position vector. Okay, so here it is the change in position vector of the center of mass. Now we know that center of mass's position is given by this summation formula. For a many particle system. So displacement of center of mass, which is change in position of center of mass, will become delta of summation mr divided by summation m. Now, for a system with particles of fixed mass, mi is constant for I going from 1 to n. So therefore, when we apply this change formula, it becomes summation of m into delta ri divided by summation of m. And further, delta ri is nothing but displacement of a particular particle. So it is weighted mean of the displacements of particles weighted with respect to the masses. So you can see that the displacement formula has a symmetry. Just like position of center of mass is weighted mean of individual positions. So like that, displacement of center of mass is the weighted mean, but of the individual displacements, not the position. It is the weighted mean of the displacements of all particles. Okay, so just quickly note down this formula. So we had seen one example of displacement of center of mass in the last lecture, albeit that example was based on a two particle system, and we had basically calculated the displacement by just calculating the individual positions of the center of mass before and after the change, and from that we had calculated the displacement. But we can see that we can also apply this kind of a concept
And
Okay, so now once we have understood how to calculate or first of all how to define displacement. Now next thing in kinematics, always from the definition of displacement we understand the concept of velocity as the rate of change of displacement or instantaneous rate of change of position. So let's apply that now over here. So velocity of the center of mass, which we can denote by a symbol like that, VCM or VC, whatever. So by definition, the velocity of any point is defined as the instantaneous rate of displacement with respect to time, or that is the same thing as the instantaneous rate of change of position, because for a small displacement, ds is the same thing as dr. And so by applying this definition of instantaneous velocity, is the instantaneous rate of change of position. By applying this definition, we understand that you get a very similar kind of formula here also. So velocity of the center of mass is instantaneous rate of change of position of center of mass. Now position of center of mass we'll again write in that summation formula. So it is summation mr divided by summation m. Now keeping in mind that all mi's are constant with respect to time. So when we expand this term, or when we operate the rate of change into this expression, it becomes summation of mass into rate of change of position divided by summation of mass, which is a constant. So velocity of the center of mass therefore becomes again weighted mean of the individual velocities for all particles. So it's a symmetric kind of formula compared to the formula for position or displacement. It's a weighted mean expression, but this time it's weighted mean of velocity to calculate the velocity of the center of mass. So this is coming from this definition. So velocity of center of mass is also coming from a weighted mean kind of expression. Okay, so now this expression is going to prove particularly important for us, because from this we will not only be able to solve questions involving application of center of mass velocity, but we'll also understand further properties and concepts related to a system of particles, like momentum and impulse momentum theorem. Yes, Jitesh, that is correct. If we differentiate this expression one more time, we can relate it with acceleration also. But as I was saying that before we get into acceleration, okay, we will also discuss about momentum of a system and impulse momentum theorem. So these are some of the important things.
Sir, can you scroll up for a moment?
Okay, people. So before we get into the concepts of momentum of a system of particles and impulse momentum theorem, let's also look at a quick example of the application of this. So this time we look at an indirect type of question, which will have a bit of application of vector algebra for you people to practice. So we have a two-dimensional system like this, in which we have three different particles. So this is our XY plane. Now let's say there is one particle which is moving like this. This is particle E, which is moving at a velocity of 15 meters per second. So that angle of 37 degrees with the x-axis like this. Let's say we have another particle which is moving like this. This is particle P. It's moving at a velocity of 12 meters per second. And finally, we have another particle C, which is moving along the negative y-axis like this at a magnitude of 10 meters per second. Now, suppose given to us that mass of A is equal to mass of B, which is equal to 50 grams, and mass of C is 75 grams. So find the velocity of the center of mass for the system ABC. For ABC as a system, we have to find the velocity of the center of mass. Okay. So this is nothing again difficult, but just for you to practice your vector algebra a little bit, and the definition of velocity of center of mass, which you can see in the formula box just above. You have to now apply that over here. This summation has to be carried out over three particles, A, B, and C. Okay, so the index I for the summation will go from 1 to 3 in this case. Just work this out quickly. I don't think it should take more than a minute or so.
Yes. So you want the mod of the velocity of center of mass or like vector formula?
Sorry, come again. We want the
You want the mod of velocity of center of mass?
no. You have to like express it as a vector, both the magnitude and direction. You can
Okay.
express it in component form if you like, or you can express it with mod and angle, right?
Yes, I will express in vector form.
Yeah.
Certain.
Okay, so let's take a look at the answer here. So we are going to first resolve these velocities into component form. Actually, only A's velocity we have to resolve. So A's velocity is becoming how
Is
much?
12
12
is
I cap,
12 I cap plus 9 J cap.
9 J cap. Very good. Okay. In meters per second. B's velocity is 12 I cap. Okay. And C's velocity is minus 10 J cap. So now velocity of the center of mass will become summation mv divided by total mass. So that is so we need not convert to kgs because the numerator and denominator, as long as they have mass in the same unit, which is in this case grams, that unit will cancel off and we'll get the velocity of the center of mass in the unit of the individual velocities, which is meter per second. So let's just work out this calculation now. So we have 50 into 12 I cap plus 9 J cap, okay, plus again 50 into 12 I cap, and now 75 into minus 10 J cap divided by the total mass, which you can see will become 100 plus 75, so 175. Right. Okay, so let's start to wind up this calculation now. So just to make the calculation simpler, what we can do here is we can probably take 25 common. So we have 48 I cap, right?
Yes.
Yes.
And we have
30.
12.
how much?
12.
Minus
So-
12. Yes.
So we have taken 25 common. So minus we have 18
No.
minus
Minus 8.
30, right? So minus 12, correct?
Yes, sir. Minus 12.
Okay, so further we can take
So we simplify 25 and 7.
so 25
1
goes
by
how many times at
1
170?
by
7.
7. Yes.
1 by 7.
7 times.
Yes.
Yes, sir.
So further we can take 12 by 7 common. We have minus, we have 4 I cap minus G cap. I think this is sufficient amount of simplification for velocity of the center of mass.
Yes.
So anyhow, this is a simple way of understanding the formula for center of mass. Okay. Formula for velocity of center of mass, how to apply it. Okay. Eventually, we might see few examples where vector algebra in 3 dimensions also comes in, but mostly it's going to be 2-dimensional at max. And in many cases, we will see only 1-dimensional applications, which are comparatively simpler. Okay. Now, next up, let's look at a very important aspect of system of particles, which we are now ready to learn because we have just derived the formula for velocity of center of mass, and through that we have learned something important. Okay. So let's see that. And that is how to define and find the momentum of a system, linear momentum. or what we can also call translational momentum for a system of particles. So we will write this symbolically as P, which is used for momentum, but for a system like this now. So previously we have seen that definition of linear momentum for a particle is mass multiplied by instantaneous velocity. We understand this from Newton's laws applied to particles or particle dynamics, that a mass m particle moving with a velocity v is said to have a linear momentum of m into v. Okay, so it's a vector quantity. So how we define linear momentum for a system now? Now we have linear momentum of a system's definition is the total mass into the velocity of the center of mass. Okay. So we'll understand the logic of this definition also very soon. But here the capital M is the total mass of the system. Okay. So you can think of M like a summation of Mi. We are talking about an n particle system this time. And of course, VCM is the instantaneous velocity of the center of mass. Now, since velocity of the center of mass was defined as summation mv divided by summation m, or that can also be written as summation mv divided by total mass. So therefore, another way to define the momentum of a system, linear momentum, is that it is the vector sum of the individual momenta of the particles. So momentum of a system can also be simply understood as summation of momenta of all its constituent particles. Okay. So while the definition of linear momentum of a system is total mass multiplied by velocity of the center of mass, but if our system consists of different particles, discrete particles n in number, moving at all different velocities, individual velocities vi, then we can find the momentum of the system by also calculating the vector sum of the individual momenta of all the particles. Okay. Okay, now next up, from this we'll understand
Just
that.
scroll up for a second.
Okay.
Last. No. Yes, sir. Hello.
Okay, done.
Yes.
Yes, sir.
Okay.
Yes, sir.
Now see, with this definition, momentum of a system defined as the vector sum of the momenta of all the particles. You can see that if we differentiate this relation with respect to time, so rate of change of momentum of a system equals to the rate of change of the summation of momenta of all the particles. So this is the same thing as summation of rate of change of momenta. Okay. D by dt of summation p will become summation of d by dt of p. Now, by Newton's second law applied to a particle, the net force on a particle is equal to the rate of change of its momentum. Okay, so
Yes.
therefore, we can denote this as Fi, where Fi stands for the net force acting on the ith particle, I going from 1 to n for the system, or ith particle of the system, you can say. So further in this definition, this becomes summation of Fi. Now we'll see one thing interesting here, that when we sum up all the forces, so this is sum of all forces acting on all particles, I equal to 1 to n of the system. Okay, why it is sum of all the forces? Because Fi itself is the net force acting on a particular particle. So Fi is the sum of all the forces acting on one particular particle. And then we are doing summation of Fi for all the particles, now from I equal to 1 to n. So that means we are adding up all the forces acting on each particle and then adding up these net forces for all the particles. So it is nothing but the vector sum of all forces acting on all particles. So when we do that, okay, sum of forces acting on all particles of the system, the internal forces cancel in action reaction pairs. And we are left with what? We are left with just the external forces sum. Okay, so that is application of Newton's third law. That if a particular particle A applies a particular action on another particle B, then B will apply an equal and opposite reaction on A. So all the internal forces within my system will be present in action reaction pairs, because they are, you know, acting as a sort of interactive force between the particles which are all part of the system. So they're internal in that respect. So they will cancel in action reaction pairs when we do the vector sum, and therefore what we'll have left with is that when we do summation of Fi, we will have only the net external force left. Internal forces cancel. So summation of Fi becomes the net external force. The internal forces don't count, only the external forces. So what we mean by external force, it is force applied by some external agent on the system. It's not a force which is acting internally within the system from one particle to another, but it is applied by some external agent outside the system on some part of the system or on the system. So that is the net external force. So it's basically the vector sum of all external forces acting on the system. So now connecting these statements, we can see that the net external force acting on a system is equal to the rate of change of its momentum. This is like a slightly modified version of Newton's second law, which is now applied for a system of particles instead of an individual particle. For an individual particle, we said net force is equal to rate of change of momentum. For a system, it becomes net external force equals to the rate of change of momentum for the system. So this is Newton's second law applied to a system of particles. Okay. And through this, we will see a lot of applications where a system might be in motion, but the net external force is zero. So it is in motion in such a way that rate of change of its momentum is zero. So its momentum should be conserved. So you would have heard of the statement momentum conservation earlier. So we will see how and when that happens and how to apply the concepts involved with momentum conservation to solve such systems where there is no net external force. So this is a very important section. In fact, the major part of the application questions in system of particles are some way or the other related to the concept of momentum conservation, which is related to the concept which we've just learned over here. That is, net external force on a system is equal to rate of change of its momentum. Yes.
Is there any day-to-day example for like no external force but internal force making the good?
Yes, so many everyday examples. Like, for example, you have, let's say, an isolated molecule, and the atoms within that molecule are vibrating, right?
Yes.
So that vibrational is force, I mean, vibrational motion is happening because of the intermolecular forces and the energy related to that force and all that, right?
Yes, sir.
But if the net external force on that molecule is zero, then the momentum of that molecule will remain conserved.
Yes, sir. And so it goes on in motion. Like how does it goes on in motion?
Yes. Okay. Similarly, collisions are example of situations where momentum is conserved for the system. Because as one object collides with another, there's only internal force, action-reaction pair, which they apply on each other. There's no net external force.
Okay, sir.
Right?
So even wire when potential difference is not applied.
Sorry, even?
Copper wire or any wire when potential difference is not applied. And the net force becomes zero.
Correct. So that is the case where, electrostatic force. Yes.
Yes, sir. Electrons are
Yes.
moving, but current is absent.
Yes, that's correct. Okay. Or you can just take, for that kind of example, you can take something very simple like this, that you have a positively charged and a negatively charged object, and you bring them close to each other and place them on a smooth surface, okay, and just place them at rest. So they'll attract each other and start moving, right? Eventually collide with each other.
Yes, sir.
But interestingly, if you take the two objects as a system, the momentum of that object will remain zero, because the vector sum of their momenta will be zero.
Okay, sir.
So means like if we take an example of anything moving but without any opposing force, so that
Without any
momentum
net
is
external force.
without an yes, sir. So the momentum is conserved and there is no external force, so it will continue being in motion.
Yeah, I mean, it might even so happen that the center of mass is at rest, it's not moving.
Yeah.
Okay. So like, for example, in my example of the two charged particles, positive and negative, attracting each other, the individual particles are moving with acceleration. Okay.
Yes.
And their velocity is increasing with time and all that. But the center of mass of the system will remain stationary. So they will finally come and collide at the center of mass.
Yes.
Understood, no?
Yes, sir.
Okay. So in fact, like we'll see so many examples of application of these concepts, so it will become more clear.
Done.
Yeah, see, Jitesh, to answer your question, whatever motion we are observing, whether it is for a system or an individual particle or for the center of mass of a system or whatever, it is always with respect to some reference frame. And generally, when we write these type of theorems of physics, we always try to express everything with respect to an inertial frame.
Hmm.
You understood the point?
Yeah, got it.
Okay, so this particular equation that we have written now, it is Newton's second law for a system of particles. And if we just invert this equation now, you can see that change in momentum for the system is equal to external force, net external force integrated over time. Okay, so if the momentum is changing from some initial to some final value in some time, some initial time to some final time. So this is called the impulse momentum theorem, that the change in momentum equals to what we call as an impulse due to that external force. J is impulse. So impulse due to a force in general is defined as integration of the force over time. So here, this J external is the impulse due to net external force. And it is nothing but the integration of the net external force with respect to time. So in a certain interval of time, the net external force has applied some impulse, that is the integration of force with respect to time. And that impulse equals to the change in momentum of the system. So this is called impulse momentum theorem. And further, as an application of this theorem, we can see that if we have a system where there is no external force, so net external force is zero. So for such a system, the impulse due to external forces will be zero. So the momentum of the system is conserved. So if the net external force is zero for a system, okay, then the external impulse becomes zero, and therefore momentum of such a system is conserved. So such a system is called an isolated system, mechanically isolated system. For such a mechanical isolated system, we have the principle of conservation of linear momentum. Impulse is defined in this way. This is impulse due to a force. So for example, if we are talking about a constant force, then the impulse becomes force into time. But if it's a general situation where the force may be variable, so it is integration of force over time.
Oh, done.
Okay, so let's understand example of the application of this concept. So let's take that case we're talking about of two objects which have possibly been given some charge. Okay, but here let me take it as if they've been given like charge. So both are positively charged. They are placed on a smooth horizontal surface, and at t equal to 0, they are both at rest. Now, as a result of the repulsion between them, as you can imagine, they'll start moving. And after some time, what we observe is something like this has happened. A has maybe reached here. By then, B has moved here. So at some time t, A has a velocity of 2 meters per second. And B has a velocity VB. Just a minute, I'll reshare the file. Okay, so at time t, this is what has happened. So the object B has made a displacement of 1 meter. This direction, A has made some unknown displacement, but A's velocity has become 2 in this direction. B's velocity is unknown. A's displacement is unknown. So blocks A and B are of mass m and 2m and are positively charged. They are released from rest as shown. So find the displacement of A and the velocity of B at time t equal to t as shown. So just try out this question. So what we'll have to understand here is that if you treat A plus B like a system, because they are on a frictionless surface, okay, and they're on a frictionless horizontal surface, so their weights are balanced by normal reaction. and there is no friction. Okay, so there is the net external force on the system A plus B is 0. Okay, there are repulsive electrostatic forces that A and B are applying on each other, but that is a mutual force. That's an internal force which cancels an action reaction pair. So that means as a system A plus B's momentum should remain conserved. Even though individually A and B are going to be moving and with accelerated motion, but the system's center of mass should have a situation where the momentum of the system is conserved. Okay. So using that as a hint, try to solve this problem now, and you'll understand what we mean by isolated system and application of conservation of linear momentum.
Sir, I have sent you the answer.
Okay, so let's work this out. So what we have to understand in this question is that this is a mechanically isolated system, right? On this system, the net external force is 0. So that means the momentum of the system. Now, what about the momentum of the system? Here, both the bodies are at rest. So that means what is the center of mass doing? The velocity of the center of mass is also 0. It's at rest. Okay. So because the net external force is 0 on the system, so the center of mass should remain at rest. Okay. And the displacement of the center of mass should remain 0 because of momentum conservation.
Like just because like they're repelling each other, the like positive charges they get cancelled. That's so.
But the repulsion has to do with the fact that is why these two bodies are moving.
Yes.
Because of the mutually repulsive force. Okay.
Okay.
But why the center of mass is not moving? Because there's no net external force. The repulsive forces are internal forces which are cancelling in action.
Yes.
Right? You understood?
Yeah.
So momentum conservation, and that momentum is equal to how much for the system? It is 0 because the system was at rest to begin with.
So
Yeah.
So, but what if the charges would have been like 2 positive charge on A and single positive charge on B? Then the system would have been different, right?
It doesn't matter, beta. System के अंदर है ना charge.
Yes, sir.
बाहर से कोई force नहीं आ रहा है. There's no external agent who's applying any force. So it doesn't matter. And here I have not necessarily said that they have equal charge. This could have any charge plus Q1 and this could have any charge plus Q2. Understanding?
Yes, sir.
But still this force and this force will be equal and opposite. No?
Yes, sir. Yes, sir. That formula.
So irrespective of how much charge A and B have, okay, this condition will remain, that momentum of the system is conserved. And because the system was at rest when it started, so it's conserved. And how much is the momentum? It's 0. No? So it will remain 0 forever.
Yes.
Okay. So if momentum is conserved, so velocity of center of mass is 0. So that means as a vector equation here, mass of A into velocity of A plus mass of B into velocity of B, this vector sum should be 0. So when we express this as a scalar, we'll have m into minus 2 for A plus 2m is the mass of B, but into VB, which we don't know. This should be 0. So this is telling me that VB is equal to 1 meter per second in the positive direction. So it's plus 1 meter per second. Okay. And displacement of the center of mass is 0. So that is now telling me that mass of A into displacement of A plus mass of B into displacement of B should be 0. So displacement of A is a negative quantity here. We'll see when we calculate. So m into SA plus 2m into displacement of B is how much now? It is plus 1 meter is equal to 0. So that means displacement of A is minus 2 meters. The minus sign is just showing us the direction. Or we can write it as a vector quantity like this. It is minus 2I cap in meters.
Yes.
Whereas the velocity of B is plus I cap in meters per second. Okay, so this is about application of center of mass concept. Okay, with momentum conservation. Okay, now people, today I'll end the class a little early here today because of some urgent personal work I have. So we'll take it from this point onwards in the next lecture, but there are a lot of problems and solved examples in HCV in the system of particles chapter, which have to do with the application of calculation of position of center of mass as well as the basic momentum conservation or that kind of principle. Okay. So I'll send you a list of few of these questions. You get started on that, and of course, if anything is pending in circular motion, please complete that also.
So,
Yes.
sir, can you please means how to know that in a sum the momentum is conserved?
This is the condition that the net external force should be 0. Just like when do we conserve mechanical energy? When there is no non-conservative force and the work done by external forces is 0, right?
Yes, sir.
So like that, when do we conserve momentum? When the net external force itself is 0 as a vector quantity. Okay?
And so the next time you will means discuss the doubts of circular motion, right?
Yes, next week's lecture, I'll keep one of the sessions some time aside for discussion of doubts.
So the momentum will
Okay.
be conserved even if the charges are different,
Even
opposite,
if the charges are,
plus and minus, negative and positive.
had it been opposite charges, then instead of moving further apart, they would have been attracted.
Yes.
And at some stage they would collide. But even in that situation, the calculation would be the same way. The displacements would be in opposite directions towards each other. The velocities would be like an approach velocity. Here they're like a separation velocity, right?
Yes.
Okay. Okay, so that's it for today's session. People, wish you all the best. Have a nice day.
Thank you, sir.
Bye.
So sir.